Oh, hello. Does this lighting work for you? It's a non-trivial optimization problem because I need some light here, but at the same time I don't want light there. And there is a little bit of light on this, so you can see, which I think helps. So I based on what I was hearing from you in terms of interest in final projects, I decided to do first the finite element method for volumetric elasticity, and then do the rigid body and collision detection, even though I just heard somebody would prefer to do rigid bodies first. But lots of people were interested in this and the projection-based dynamics. By the way, I posted the paper on Piazza, the link of the paper on Piazza, but please don't distribute it anywhere because it's still unofficial and unfinished. The information are there, but it's not the official version at all. And that paper is also basically a different way to solve implicit Euler time stepping for finite elements, even though in a little bit modified way. So I wanted to cover the basic material about volumetric elasticity. The good resource is this. That's what I will be basically following course notes by my colleague Eftichios Ifakis from Wisconsin. And this document you can download for free right here, FEM-Defo. There's a second part of the tutorial. This was a course, SIGGRAPH 2012 course, and there's a second part on model reduction by Jednej Barbic, which is also pretty cool, and that's sort of advanced material. I don't think I will be covering the second part unless you were specifically interested in that. But this is the basic material. Okay, let me remind you that you need to make your decisions on final projects by Friday. And that means two things. First, I need to approve on your idea. And second, you need to submit that idea that has been approved and the list of team members on Canvas. And you only need to submit it once per project. So if you are like 3 members in one team, then only one of the team submits it for all 3. Okay? That's what I was already explaining on Monday. All right. And if you want to discuss with me some final projects, have a little bit of time after class, then I have to meet one student, but then I have some more time, so I have office hours today from 3 to 5 as before. So you're welcome to talk to me about your project ideas. But you can also email me and we can discuss over email. Okay? Any questions on final projects? Did I forget something? Yeah, fluids are still due on Monday, right? Let me just remind you. Your final fluid homework. Okay. So let me first motivate this. Why do we care about volumetric elasticity? When you already know how to do Jello, right, with mass springs, just connect points with mass springs. You already know 2 ways how to solve them. So why don't we just use that? So if I have some 3D object, I can tessellate it using tetrahedra, do tetrahedralization. There are some tools for that. And like if I have some, okay. Let's assume I have some object. And that's some elastic material, and if I'm looking at one small piece of that elastic material, that's essentially my finite element. It's some something that mathematics would want it to be infinitely small, but we don't really want it infinitely small, so we will just assume it's finitely small, but it's like really small, just like tiny piece of a material, just like when you're dealing with triangle meshes, right? Those are very tiny piecewise linear representations of the surface. So here we are looking, it's volumetric, so you are looking at the solid, at the actual volume of the thing, okay? And if I have tetrahedralized the entire volume, so imagine this all lives in 3D, then the small element will be one tetrahedron, right? And the simplest thing you could do, just apply what you already know, right? Just use a mass spring system. So just say that these are my particles, and just put, and I say that these edges are springs. You could do that, right? And that actually works reasonably well. That's exactly how Tintin did the frog shoot, if you remember that. Do you remember the frog shoot? But the thing is that this does not give you particularly accurate control over the material properties. It's good enough for shooting frogs and things like that, for like games and some entertainment applications. But if you want to better control the material parameters, then what would you do? What can you control here, right? You can control the stiffnesses of each of these springs, right? But if you would want to, for example, say that this tetrahedron should not compress to 0 volume, that would not be so easy to do, right? So if I have any elastic material, so I am basically elastic material for most parts, right? You are too, like human body, except for bones, which are sort of rigid, but also not perfectly rigid. In the real world, there is no such thing as a rigid body, right? Rigid body is just an abstraction. Every object is elastic to some extent. When I was walking to work this morning, I saw this traffic light in the wind, and it was like, it was bending quite a lot. So something you would expect to be rigid is not really. So everything is elastic to some extent. And absolutely no real world material can compress to nothing, right? Because at the atomic level, there are some particles, and you just cannot squish them to nothing. Even air, right? You can compress it quite a lot, but you cannot compress it to nothing. So if I have a small element of my material like this, and I want to impose a constraint that it doesn't compress to nothing, how do I do it with a mass spring system? I can give it stiff springs, right? That's probably the best I can do. But that's not exactly saying the same thing. Some people, a specific problem is that if this tetrahedron flips on the other side, like an umbrella, if I just flip it upside down, then all the springs are at their rest length. They are perfectly happy there, right? Just if you have an umbrella, right? It's normally this shape, but if there is a lot of wind, it can pop on the other side, and all of a sudden it's perfectly happy there. Doesn't want to go back. That's the problem, right? If it wanted to go back, it would just like pop back in a little bit, but it doesn't do that. So mass spring systems behave exactly like that, right? Once it pops, because there is lots of external forces like wind or something, or in simulation some collisions or something like that, just pops to the other side and stays there. That's not good, right? There were some tricks developed for mass spring systems. One thing, I think it's called altitude spring, that you can define an extra particle here, connect it with some springs like this, and do another spring there that will make the tetrahedron like a little bit stiffer, because this spring now acts against compression of the tetrahedron. But it's, again, just a hack, right? And now you have another problem. How do you select stiffnesses for these edges, right? Good luck picking that. And that's different for every single tetrahedron, potentially, right? And also depends on the shape of the tetrahedron. It's usually not going to happen that all tetrahedra would be nice, beautiful tetrahedra like this. You might end up with some weird slivery things like this, right? That this is perfectly valid tetrahedron. Not so beautiful to set parameters for it. Because this wind spring is super short, and these others are much larger. Also, maybe I should have shown the projective. I can just draw it quickly. Also, if you have something that's for some reason not tessellated uniformly, so if I have some sort of sheet and I need a lot of precision here for some reason, and I need much less precision further away, then I can just put big triangles over there. In computing, they do that quite a lot, right? If you have, I don't know, like a plane and you only care about the engine, then you are probably not meshing the entire plane with the fine resolution. You only use the fine resolution on the area you really are interested in, right? But then if you want to do it by a mass spring system, it becomes a nightmare setting the parameters, right? Because these larger springs should have different parameters than the smaller ones, and it's not as simple that you would just scale them linearly, it would work, right? You can imagine it's more complicated than that. So finite element method, FEM, is essentially the principled way around all these problems. And it's derived from continuum mechanics. Actually, before this tutorial was done, the best resources were really like mechanics textbooks. That's what like folks in, maybe some of you are from mechanical engineering, I'm sure there are certainly some courses on specifically on that. But these textbooks are usually pretty old school and not so fun to read. There's like, I read some of these books and I learned nothing about that. If you read this tutorial, you will learn pretty much everything about it, everything you need in physics-based that way. Okay, so what are the main ideas here? So we will be looking at hyperelastic materials. So that means those are materials which are happy at some pose, which is the rest pose of the material, some undeformed pose, and the material always wants to return back to that rest pose. So I will be drawing examples in 2D, but all of the things apply in 3D. So if I have some rest pose, let's continue with my evil bunny example. So this is this is my rest pose shape. Let's call it omega, and the omega is just a subset of R2, right? That essentially says what is the solid shape I'm looking at the undeformed rest configuration. So the energy associated with this configuration is 0. That's where the object naturally lives. So in 3D, of course, that would be a subset of R3, right? And then if we subject this to some simulation with some external forces and whatever, then it means that the object deforms. And we can explain the deformation. You know what, let me put there all 3's, and you will understand that the figures are just for illustration purposes in 2D. So the function f is a function which maps it from the undeformed space to the deformed space. So let's say I am torturing this shape, and it's subjected to some deformation. That's what the function f does, right? It takes a point from there, maps it to a point there. So here I get f omega. That's the image of my rest shape, right? And the most important concept here is the deformation potential, the deformation energy associated with this deformation f. If you think about it, it is really just a refinement of the very basic idea of the spring, right? When we were looking at a spring, we had a rest pose. Maybe let me put it here. We had a rest pose spring defined by 2 particles and some rest length r, right? And then I was saying if the spring is extended, for example, or compressed, let me give this tildes to say that these are in the rest pose and these are now in the deformed pose. So if the spring is extended, then there will be some elastic energy associated with it. Basically, there is some elastic energy stored in that object, if you will. If you let it go, it will do something, right? And settle at the rest. That's the intuition you can have about that. In the case of the spring, we knew that the energy was, how much was the energy? P1 minus P2 minus R squared, right? With some coefficient. So what continuum mechanics and finite element method applied to volumetric elasticity basically is generalizing the spring case to an arbitrary shape case. So what do we need to now figure out is what is the energy associated with the function f. So some EF thing where this EF is going to be just a non-negative scalar, right? It's energy, so it should not really be negative. That wouldn't make much sense. But the idea is that if this energy E is large, it means that the shape is stretched a lot, right? If it's small, then it's stretched just or compressed or deformed just a little bit. And if it's 0, then it means it's exactly at the rest pose. Or a rigid body transformation of the rest pose, right? If I just translate it or rotate it, the energy of the translational or rotational deformation should be 0, right? That's quite important. That will come up later. And by the way, this E is actually a functional, right? Because as input, it takes a function and it returns a scalar value, which is sort of interesting. Here it was just a function, right? It was just taking two vectors and returning a value. Here, the continuum mechanics works with continuum, so f is a real continuous function. But this is sort of just like a mathematical interesting thing. We will not really deal with the continuous view for too long. So the assumption of hyperelasticity, we will assume that our materials are hyperelastic. So that means several things. It means it never breaks or deforms plastically, right? Real world materials are never like this, right? If I just deform this, eventually it would break, which means it would essentially change the rest pose, right? There's also plastic deformations, like in cloth or something, or what would be a good example? Play-Doh, right? If you just push on it, then it just changes its shape, and it's perfectly fine there, which corresponds to changing, one way to explain this is by changing the rest pose. For simplicity, we will assume just hyperelastic materials which don't do that, which always want to return to the rest pose and never break. There are, of course, methods in computer graphics how to do fracture, how to do all these effects, but that's another story. So how can we define this energy? That's the main topic of the lecture today, I suppose. So the continuum view is to define a function which is called energy density function for a given deformation field and for a given rest shape point x. So in this case, my x with tilde, I give the tildes to the rest shape quantities. That's from my omega. So here, so some of these points, maybe this point would be x tilde, right? And the fx tilde maps it to some x, where x is f of x tilde. The standard notation in continuum mechanics is to use uppercase for the rest pose. So like use uppercase x for the rest pose and lowercase for the deformed pose, but I think it's a really bad idea because it's sort of difficult to tell which is lowercase and which is uppercase. So that's why I give it the tilde. So tilde means from the rest pose. So if somebody gives me this energy density function, so this tells me, this characterizes the deformation locally at every single point. So then to compute the deformation of the entire shape, what do? I integrate over the entire omega. So I integrate the deformation density function for a given deformation f for all rest pose points dx. So you can look at it as taking like small pieces of the material, probing for given f, for given deformation, and probing the psi and integrating, summing essentially all these small elements together. And what this energy density function is, it's deformation energy per unit rest pose volume. So how can we define reasonably this function sub psi? So look, it turns out that looking directly at f is not that useful, because we only want to characterize deformations of the material, right? So for example, if the entire thing just translates, there should be zero deformation energy associated with that, right? So the idea is, instead of looking at f, we will be looking at, guess what, the Jacobian of f. So what is the Jacobian of f, or equivalently gradient? It's a vector function, so usually you call it Jacobian, but some people also call it gradient of a vector function. And you should remember from the first calculus classes, so if I say that the f is a collection, let me make it very clear. So the f is a collection f1, f2, and f3, where all of these fi's are from r3 to r, right? Just split it in coordinates. And then the Jacobian is just f1 by x, f1 by y, f1 by z, and the same for f2, f2 by y, f2 by z, and here is f3, f3 by x, f3 by y, f3 by z. So the Jacobian is a 3 by 3 matrix, right? And sometimes it's also called the deformation gradient, and it's written as capital F. So that's the same thing, that's just not in notation. It's a 3 by 3 matrix. And what does this tell us is, so you know what you should know what Jacobian is, right? It's a local linearization of my function. So this means it's looking at the behavior of my deformation field f, which can be completely arbitrary. It should be differentiable and continuous and so on. But certainly it doesn't have to be simple, like linear or anything. It can be this, right? But what this means is that I will look at, if I have like some small neighborhood, I will look at the deformation of a small neighborhood of my material point and the corresponding world space point. So probably it will make more sense if we switch to the discrete settings. So you could continue in this way and develop all continuum mechanics in the continuous world. Just keep working with the deformation gradient, keep as a continuous field, keep integrating it, and so on. And eventually, at some point, you have to discretize, right? If you want to solve it on a computer. It's fine if you just want to prove theorems, you can stay in the continuous world forever. But at the moment you want to actually compute something, you need to give it some finite number of degrees of freedom. So we can as well do it straight away. And what we are going to do, we are going to do it assuming that the rest shape has been tessellated using tetrahedra, so tetrahedralized. Okay. And I will show you how to compute the deformation gradients on a tetrahedron. That's sort of interesting. So let's assume that omega is tetrahedralized. Of course, you could also study this in 2D. In that case, you would only do triangle mesh. If for some reason you were interested in 2D deformations, most likely you'll be interested in 3D deformations. So that means I'm looking at individual tetrahedra, and we will be using linear finite elements. What that means is that on every tetrahedron, f is linear. So what that means is before I was saying that the F can be completely arbitrary mapping. Here I'm saying that no longer arbitrary, the F needs to be linear on every tetrahedron, so altogether it's piecewise linear. Yeah? And because I have now a finite number of tetrahedrons constituting my shape, then I need to look just at one tetrahedron, and then I will just sum the contributions of all tetrahedra together, right? So because the F is linear, that means that on every tetrahedron, it is mapping a rest pose point x tilde like this, where this F is our 3×3 deformation gradient, and B is some translation, some vector 3×1, right? Because if I have a 3D a linear, that's actually a affine function, then it must look like this, right? And this is exactly the deformation gradient, because the Jacobian of this is exactly F, right? Because this is just a linear part there. And this translation disappears immediately. So how does it work? So let me draw some example tetrahedron. So let's assume this is my tetrahedron in the rest pose, like this. Let's say this is x1, tilde, x2, and x3. We have to figure out how to compute the deformation gradients, so we can actually compute it. So this is one of my rest pose tetrahedra. Then I would loop over all the rest pose tetrahedra and repeat the computation for all of them. And the mapping F maps it into some deformed tetrahedron like this. So you can be looking at it as like a small piece of the volume, like small chunk of the material, and we are looking at the deformation of this particular chunk of the material, which is specified now just by a affine function F. Okay, so that means it takes this rest pose tetrahedron and maps it to some other tetrahedron. And we need to find out what is the deformation gradient, the capital F, of this mapping, lowercase f. Here we have another lowercase uppercase, but at least here you can sort of tell which is lowercase and uppercase, right? So how do we compute the capital F? We assume we know what these x's are. We assume somebody told us the current deformation of the shape. We of course know what the rest pose is, right? That's what we are given. And then, so then we can just write that x1 is, let me try this. Some more writing here. So that's this plus b. I will get rid of the arrow. x2 is of course the same thing, right? But I want to write it explicitly. x4. That is just saying that all of the points are mapped by the same affine transformation. Okay? So how do I recover the capital F? Maybe somebody could tell me that. Or maybe it's not so simple. So first I can subtract the last equation from the first three. Are you with me? If you have some questions, feel free to just interrupt me. So I'm subtracting the last equation from the first one, so I will get this. So I will get f x1 tilde minus x4 tilde. Then I will subtract it from the second equation, and I will get this. Oh, and I forgot the tildes here, see? And this. So notice an interesting thing, the b disappeared, right? Because that's it. That's exactly the reason why I was subtracting it, because if I take this equation, subtract this equation, this b minus b falls out, right? So that's sort of the point of the deformation gradient, that the translation disappears. Doesn't matter at all if this tetrahedron is here or over there, right? Because essentially what all we are looking at is x1 minus x4, right? So what is x1 minus x4? That's this arrow, right? x2 minus x4 is this one, and x3 minus x4 is this, right? So we really want to be looking only at the deformation of the tetrahedron. We want to characterize how much it has been deformed, and that's what we are. That's why we are deriving the deformation gradient f. So now observe this. So these are all vectors, right? Both the axis and the tilde axis are 3x1 vectors, right? So I can put it all together into one nice matrix formulation. I can rewrite these equations using one matrix equality, like this. So that means I take these vectors and put them as columns into this matrix. That's going to be, of course, a 3x3 matrix. And we will call this DS matrix, like shape, deformed shape, if you will. Now this is my F. And here are the right-hand sides. x2 minus x4 and x3 minus x4. So you see how these three equations are equivalent to this one matrix equation. Let me denote this as dm, like material matrix 3x3. I think I'm sort of following the notation of the FEM Defo tutorial. So if you are reading the notes later, they should make sense right out of the box. So also 3x3, of course. So this is a well-defined matrix equality, right? It says this matrix on the left needs to be equal to this multiplication of F and dm. And it should be obvious why this is equivalent. Is it obvious? It is obvious. So I can write it in an elegant way like this, right? Using this notation. ds equals F dm. So the ds, that depends on the current deformed state, right? The dm depends on the rest state, which does not change in hyperelasticity. So what I can do, I can just express f from here, just like this, and just invert the dm. And the interesting thing is, because the dm only depends on the rest pose, this means that I can pre-compute this. Right? During the course of my simulation, the dm will not be changing, so obviously the dm inverse will never be changing. So this inverse, I only need to compute once in pre-computation, which is sort of nice. It's a 3x3 matrix. It's not a huge deal, but it's still good to pre-compute that. More importantly, it's good to, or let me ask you this way, could it be singular matrix? Because matrix inversion doesn't have to always work, right? So you should be worried, hey, what if the inverse does not exist? What if it's a singular matrix? What does that mean if it's a singular matrix? Anybody?
So the columns will be linearly independent.
That's right. And what does it mean for the element?
They can lie on the same.
Right. So that means that's a really bad finite element, right? It's only a property of the rest pose. So if you get an element which would have a singular matrix dm, that means that's an element with zero volume. So it's a really bad finite element, right? So what you should do is to download the different library for the tetrahedralization, because if it gives you a singular or elements with zero volume, then it was a really bad tetrahedralization. So that's good, because if you have a good tat meshing software, it will give you matrices dm which you can always invert. And now you know how to compute the deformation gradient f for an arbitrary and deformed configuration, as long as it's piecewise linear and described using linear tetrahedral finite elements. Okay. So how does it tie back to this formulation? It actually ties back to this formulation quite nicely. So take a look at this. Because the f is linear on my tetrahedron Ti, let's just call the tetrahedron Ti, that means that if this is a linear function, that means that the capital F is constant on the entire tetrahedron, because I assume that f is a linear function. Then the deformation gradient on the entire tetrahedron is constant, right? So that means that my psi, my deformation energy density, is also constant on the tetrahedron Ti. And therefore I can write this. I can compute the total energy as summing over tetrahedra. So let's say that I index is my tetrahedra, and this is integral over tetrahedron Ti of my energy density function psi. The energy density function could in theory be different for every tetrahedron, right? So let's assume that. Let's say that the energy density function depends only on the deformation gradient. That's the typical case. And I integrate over the rest both. So because the psi is constant there, that means I can write this very easily. I can write this just as Wi, which is the constant. That's the volume of my rest both tetrahedron, times this, right? Because if I'm integrating a constant function, it's just the volume of the domain over which I'm integrating times the volume, right? It's like the simplest case of integration. And what is the Wi? The Wi is the volume of the tetrahedron, which I can nicely write like this: the absolute value of the determinant of this dm matrix for tetrahedron number I. That's just a formula for volume of the tetrahedron, right? You should know that the determinant of this matrix, or this matrix dm, gives me exactly 6 times the signed volume of the tetrahedron. The signed means that the orientation matters, that if you have the tetrahedron oriented in the wrong way, you will get negative volume. So the absolute value gets rid of that, because volume, of course, should be positive function. Okay, does that make sense? So here you can actually see how this already is sort of taking care of the small elements and big elements, right? Small tetrahedra and big tetrahedra. Well, here this volume, right? That big tetrahedra will be weighted by big W, and small tetrahedra will be weighted by something small. So that sort of makes sense, right? Now, of course, you might be a little bit confused about what exactly is this psi, right? Why is it different for every element? That should be sort of obvious, right? If I have something like a human body and I discretize it with like a million tetrahedra, then some of the tetrahedra will correspond to bones, some of them will correspond to muscles, some of them will correspond to fat tissues. Each of these materials has different deformation properties, right? And that's why I assume that every tetrahedron in general can have different deformation properties. So that's why the psi I. If you'll be playing just with homogeneous material, then you can just say that the material is the same for all tetrahedra, and in that case you don't have to index here by I. You always have to index here by Fi, because the deformation gradient for every tetrahedron can be different. Okay? So we need to look what are these functions psi, the deformation density functions. So it's a function that takes the deformation gradient, which is a 3x3 matrix, and gives me a non-negative scalar. And essentially it combines two things. It combines a strain measure. I will explain what it is in a second. Strain measure and material model. So the strain measure will be more obvious from the formulas we will look at a little bit later. But the strain measure means just the deformation itself, and the material model means the energy associated to a specific type of material. But I guess you can as well forget about this distinction and just assume that it basically measures deformation. In our discrete case, deformation of one tetrahedron, right? So if this is like a big number, that means that this tetrahedron has been squished or stretched or deformed a lot. And if it's small, if it's 0, that it means that it has not been deformed at all. Okay? And now the main fun of continuum mechanics consists in choosing different energy deformation density functions, different psi functions. So let's take a look at that. So how to define the psi? So again, psi is a function of the deformation gradient, and some sort of has to evaluate how much the deformation gradient is deforming things. So how about this? How about I say it's some k-half, that's some constant, that's not interesting. What if I just take the Frobenius norm squared of my deformation gradient? So don't be confused by this f, that just means f for Frobenius, and this is f for the deformation gradient. So what would this energy do? So if I gave it some rest shape and said minimize this deformation energy, what would it want? What is it taking? It's taking the Frobenius norm of every deformation gradient, right? So when it will be 0. You know what Frobenius norm is, right? Frobenius norm means sum all the elements squared and take a square root. This square root, that's what I'm canceling by this, so no square root there, right? So this is only 0 if the F matrix is matrix of all zeros, right? So that turns out this energy is not terribly useful, at least not directly useful, because what would that do? That would collapse the entire bunny or whatever shape we have to a single point, right? Wants to collapse everything to nothing. So it wants to collapse my tetrahedron, shrink and shrink and shrink, and it gets 0 if all these vertices shrink to the same point, shrink to absolutely nothing. So this energy is not useless. It's actually quite useful if you combine it with some external forces, with some other constraints. Because if you say, we just used it for a project on image warping. So if you have a 2D domain and your 2D domain is an image, it's perfectly reasonable to minimize this function as long as you say that the edges of the image, they must not move, that they stay put, that they stay where they are, right? Now, once you say this, now it makes sense to minimize this, right? Because it would want to squish everything to one point, but it can't because there are some external forces acting on it. I guess you can physically imagine it. Imagine that you have some sort of membrane that's like under tension, and anytime it's non-zero area, it's under tension. But if you put there a frame, if you build like a steel frame or something and attach the membrane to the borders of the frame, then it cannot go to nothing, right? Cannot squish to one point. So then it starts doing something interesting. Nevertheless, this is not an example of a hyperelastic material, right? Because I said that hyperelastic materials need to go back to the rest pose, right? So what do you think would be the simplest possible energy which would have the property that it's 0 at rest pose? By the way, notice that this doesn't care about the rest pose, right? Just wants to make every deformation gradient 0. So whatever the rest pose wants, it wants to go to a single point. So do you know what would be the simplest energy? So I'm like writing examples of deformation energies. So what would be the simplest one that would be really hyperelastic? That would be 0 at the rest pose. So what does it mean? At the rest pose, my deformation gradients are what? If I am undeformed, all the deformation gradients, all these matrices F will be trivial, right? But they will be. Just shout it. Well, they won't be 0 because that would transformation by 0 matrix means transforming to 0, right? But they will be the next simplest thing. They will be identities, right? Because if this triangle is exactly this triangle, then the affine transformation is identity, and I will get, and my F will be just identity, right? Because this ds will be exactly dm, so I will get dm inverse, so F will be identity. Also, I need to define energy such that for F equal identity, I will get 0. So what do you think is the simplest way to do that? Again, I'm probably asking 2 stupid questions. Obviously, the simplest way to do that is to just subtract identity from the deformation gradient. Right? And this is the simplest linear material that actually makes sense, in the sense that it respects the rest pose. It doesn't want to collapse to 0, but wants to collapse back to rest pose. So if I have some shape and I deform it, this energy will be saying, well, just go back the straight way back to the rest pose, back to my deformation gradients being identities. These cases are always just some positive scalar parameters. So this is the simplest energy that works, but it has a problem. Remember that I said that this energy E should not really change if I translate my shape, right? It should also not change when I rotate my shape. So it will never change if I translate. That's because I am making it only dependent on the deformation gradient, and the deformation gradient is already blind to translations, right? Why is it blind to translations? Well, because here I subtracted, so whatever translation was there got cancelled, right? Fortunately, the deformation gradient is not quite blind to rotations, right? So imagine if I take this shape and like rotate it, I will get a different deformation field F, but I would want the E of this rotated F to be the same, right? Because of course the deformation hasn't changed at all, right? I only turned the shape around, so the deformation energy needs to be the same, right? Unfortunately, that's not the case with this energy here. Why is that not the case? Well, imagine that F is just pure rotation. So imagine that F is just R, where R is a pure rotation, so SO3. So I don't deform anything at all, I just rotate it. So I don't even go to some deformed thing, I just take the rest pose and just turn it a little bit by some global rotation R, right? So what this energy will tell me? Well, this energy will tell me, well, now you have there R minus identity, probably is now squared, right? That's not going to be 0, right? Why would that be 0? Because this is a rotation, that's not identity. So that means that's bad. That means this energy penalizes rotation. It basically does not understand the difference between deformation and rotation, or in other words, it treats rotation as a type of deformation, which is not good. There's a lot of work in early physics-based animation, like early 2000s. I guess now I'm showing my age. where there was a lot of papers dedicated to this problem, because the simplest form of elasticity is linear elasticity, which is essentially a simple variation on this. We will get there in a little bit. And it has the problem that under large deformations, like deformations in a human body, these are under large rotations. So these are large rotations, right? You can easily like make 180 degrees rotation. That's large rotation. If it's like plus minus 5 degrees, that's not a large rotation. But under large rotations, this energy introduces problems, exactly because it does not see the difference between rotation and deformation. So what it ends up doing, it prefers deforming things rather than rotating them, which, as you can imagine, creates artifacts. So how can we fix that? So my third attempt would be, now I want rotationally invariant psi. So what I want from my next attempt of psi is this. I want, if I take an arbitrary rotation and after I'm done with my deformation, I rotate it, I should get the same energy as if I did not rotate it, right? And that should be true for any, no matter how big rotation, right? So the idea is, if after my deformation, I turn it, I should get the same energy, right? You see, obviously that's not true for this energy, right? Too bad, because this is a nice, easy quadratic energy. So do you know how could we do that? By the way, in a mass spring system is rotationally invariant, right? Because that's the beauty and also the ugliness of this equation. That's why it's complicated, but that's also nice about it, right? Because if I just rotate the spring, well, I'm just measuring the length, right? So the length is gonna be the same no matter how I rotate it. So we need to get the same behavior here. Actually, you don't always need it. Like when people are doing like finite element analysis of something like this, something that's almost rigid, right? Like this table or some piece of an airplane or something like that. That they can do finite element analysis on that. And there it's perfectly fine to just use linear material, because there will be some deformations, but they will be small. So the rotations will also be pretty small. So in this case, it's okay to use linear elasticity. But in graphics, quite often you need to spin things around quite a bit. So more often than not, you really want to be careful and make sure to have rotationally invariant psi. So how can we do that? What would you suggest? This is a non-trivial question. So again, it has to be some sort of matrix formula like this, right? But now it needs to be something smarter, so it essentially cancels out whatever rotation comes there, right? So what do you think is the simplest way to essentially become blind to this rotation? So the simplest way is to use whatever is called the Green's train. Just a fancy name for a very simple idea. Idea is this. And watch this. You just do FTF. And that does it. So why does this work? Well, if I take this psi, I guess I should like index them like psi 1, psi 2, psi 3, but I hope you understand that it's a different energy in every case. So well, if I now plug their RF, then what I will get? Well, obviously, FT FTRT or F minus identity, Frobenius squared, right? But RTR is identity, right? So that disappeared, so that's good, because that means that's this. FTF minus identity, Frobenius squared, which is exactly psi of F. So that's exactly what I wanted here. So that's the simplest way to achieve that. Okay? And that's almost San Venant-Kirchhoff material. I will, not quite, there is one piece missing, which I'll explain in a minute. So here the main idea was to do this FTF. So this idea is called the Green's strain idea. So the Green strain sometimes also denoted as E. So I don't like it because it looks like energy, even though it's not energy, it's just a strain measure. And that's FTF minus identity. Because sometimes, especially in continuum mechanics, people do it like this. From the deformation gradient, they define a strain measure, like the Green strain, and then the deformation energy density depends on the strain measure, E, which then in turn depends on the deformation gradient. And guess what? The deformation gradient depends on your deformed configuration, and that's the end of the dependencies. But you don't have to worry about this too much. Okay, so that looks good. There is a problem with this. The problem is that now it's little too much invariant. The problem is that if I take the problem is it's not invariant just to rotations. It's invariant to all transformations that have this property, right? And unfortunately, that's not just rotations that have this property. What other matrices have this property? Also reflections. So if I take this, for example, so let me take a deformation gradient like this. 1, 0, 0, 0, 1, 0, 0, 0, minus 1. If I do FTF, I will get, of course, identity, because this is minus 1 times minus 1, right? All of a sudden, I have 0 energy, right? So this energy becomes 0 on this particular F matrix. What is this matrix? That's a reflection about z-axis, right? So reflection means if I have an object, then just reflects it like this, right? Just makes z go to minus z, like mirror. So that's again a problem, right? Because that again means that's our umbrella effect essentially, right? If I flip it, if I mirror it, this energy will be invariant to the reflection. So yes, it is invariant to rotation, that's what we wanted, but unfortunately as a side effect, we also obtained invariance to reflection. So we still need to think once more and come up with an energy which is rotationally and only rotationally invariant. That it will see the difference between one configuration and the reflection of the configuration. So it will want to push the umbrella back to the undeformed state. So in other words, it will if it gets a matrix like this, it will say, oh no, this is not a 0 deformation energy, that's non-zero deformation energy. Put forces to go away from that, right? Actually, as I mentioned, forces again, this thing always applies, just like in springs, right? Forces we get simply by differentiating this deformation energy with respect to our degrees of freedom. I will explain that in more detail with more formulas later. But again, it's the same idea. Forces are always derivatives of the energy. So how do we get the best, I guess I could say the state-of-the-art energy that's used in physics-based animation? Has been introduced in 2004 by a paper, I think also from Stanford, Jeff Irving and some guys, and Ron Fatkill. So what can we do? How can we differentiate between a rotation and reflection? So again, we need to look at the deformation gradient, right? And we somehow need to analyze it to realize if there is a rotation going on or if there is some reflection. If there is rotation, we want to ignore it. If there is reflection, we want to not ignore it but penalize it. Because penalizing it means that there will be restorative forces that will want it to uninvert, right? Forces that will want to bring this flipped house back to the non-flipped house. So what is the panacea of linear algebra? SVD, right? So how does it work here? So we can use SVD to decompose our deformation gradient into these matrices, into U and V, which are orthonormal matrices. So U and V are 3x3 orthonormal matrices. So that means that UTU is VTV is identity. And the sigma is the matrix of singular values, right? So the sigma is a matrix that looks like this. Sigma 1, sigma 2, sigma 3, 0, 0, 0, 0, 0, 0. So now, these don't have to be rotations. So actually, first of all, how can we detect that the element is inverted? Even before doing the SVD. You can just look at the determinant. Right? Because what does it mean? If the determinant of f is 1, then it means that the element did not change its volume. Right? If the determinant of f is 0, that means that the element has been squished to 0 volume. If the determinant of f is less than 0, that means we have an inversion. Right? So let me actually change this a little bit. Let's assume I have a... Let's see, how do I put this argument? Let's take a look at this. So my determinant of f, if I have the SVD, will be the determinant of u times determinant of sigma times determinant of v transpose, which is the same as determinant of v, right? So I need to do something if the determinant of f is negative. Here is the catch. So the standard SVD does not give us rotations as U and V, right? The reflections can be present in the U or V. So let's see how could I fix the SVD so that this U's and V's, they would be indeed rotations. Because that's really the point. I want to isolate the rotation of the element from the reflection. And I can do that using SVD, but I need to be a little bit careful. So the thing is that the sigmas in the standard SVD have this property. Right? We had this sigma recap, so you must know this. If it's a non-singular matrix, then this will be strictly greater than 0, right? But in all cases, this will be non-negative, right? So if this is negative, it means that either the determinant of u or the determinant of v will be negative, right? So let's assume, for example, that we have a reflection in u. The determinant of u is -1. By the way, because these are orthonormal matrices, the determinant can be only plus or minus 1, right? So let's assume this case. Let's assume the determinant of u is negative. So here is what we can do about that. We can define some u prime, which will be u times this. 0, 0, -1. And then I can define sigma prime. I'm sort of trying to fix for the fact that this is not a proper rotation. I'm trying to isolate the rotation from the reflection. 1, 0, 0, 0, 1, 0, 0, 0. That's the same matrix. That's basically this matrix. Like this. Now notice that after this definition, the whole point of it is that u prime sigma prime is the same as u sigma, because if I multiply them together, this matrix becomes identity, disappears. And why I'm doing this is because the determinant of u prime is minus determinant of u, because determinant of this matrix, of course, is -1, minus determinant of u, which is now 1, because I assume the determinant of u is -1. If I negate it again, I get 1, right? So if I use this modified SVD, if I use this decomposition, u prime sigma prime vt, I did not touch the vt because I was assuming that the determinant of v is okay, it's 1. Then what happens now? Well, this u prime now is a perfect rotation. Let me write it again. Visible. U prime is rotation. V is rotation. And something interesting happened to sigma, right? The sigma prime. What is sigma prime? It's sigma 1, sigma 2, and minus sigma 3. Because sigma prime is this matrix times this. So that means that the last sigma got multiplied by -1. And here is where I see the inversion. If I get the last negative, if I get the last element negative, this essentially reveals that something got inverted there. And then the u prime and v, they tell me in exactly in what coordinates they got inverted. Yeah, did I get something wrong?
If there are two reflections, that means if f is 1, -1, and -1, the determinant will be larger than 0. And
correct. You mean if both? Yeah. That's a good question. You mean if both? You mean this, right? If u and v are both negative.
Yeah.
Is that what you meant?
Yeah.
Right. So that's sort of cool, because what you can do, you can use this matrix twice. You can use it to multiply both the u and the v. Okay, I can do it properly if you want. So you know what? Let me denote this matrix as, I don't know, I. So I can denote u prime as ui and v prime as I v. It's a little bit funny because it's transposed, the v. Okay, let's say it's v transpose prime. So that would be v transpose I, and then it should work like this. I should be able to do u I sigma I v transpose, right? And then if I take this essentially means negating the last element twice, so it will stay the same. And this way I make this is gonna be the u prime, and this is gonna be the V prime. Maybe I got to transpose this wrong. Maybe I wanted to put it here. But the point is that the determinant of this will be positive. Because if they are both, that's both reflections, that this basically cancels out. Or
I mean, do you use determinant of f less than 0 as some condition to initial the following?
No. This was just the reasoning behind this. So what I will end up doing at the end of the day is this. I compute SVD, I get my UV and sigma, the standard SVD, right? Now the problem is if the determinant of U or the determinant of V is negative, right? Then I need to fix it. And the way I fix it is using this trick, which as a side effect will negate the sigma 3 in some cases, right? In this case, it actually will not negate the sigma 3 because it will get negated twice, so it will not get negated, right? So this is what I will do, and then I will use the fixed SVD. The SVD, so let me make it more clear here. Still have 10 minutes, right? This clock is not valid, so that I can still probably explain it properly. All right. Woohoo. My hand is no longer there. Okay, apparently the there we go. So this last piece will be recorded. That's not clear, but if it won't, I can just repeat it next time. Okay, so what I was gonna say is after I have this rotation fixed SVD, in the sense that the SVD now works like this. It gives me U prime, sigma prime, V prime transpose, where the U prime and V prime, they are proper rotations. So no funny business this with negative determinants. That means that the determinant of U prime must be +1, and so must be the determinant of V prime. Now the property I lose is that the sigma prime now will be sigma 1, sigma 2, and sigma 3. It will still be true that sigma 1 is at least sigma 2, it is at least sigma 3, but now sigma 3 can be negative, right? Because I must be able to decompose arbitrary matrix F like this. I'm able to decompose arbitrary matrix F like this. So if the U prime and V prime cannot take the negative determinant, then the sigma prime must take it, right? And the way it will take it that both sigma 1 and sigma 2, they will always be non-negative, but sigma 3 will be negative, and that's exactly what will be indicating the inverted configuration. Does that make sense? And the way I define my deformation energy, that's my attempt number 4, and that's the one that's really good. Then after I computed this corrected SVD, I do simply this. So that's basically the same thing as saying that I do this, right? I do sigma 1 minus 1 squared plus sigma 2 minus 1 squared plus sigma 3 minus 1 squared. And you can see that if I have an inversion, so if I have, for example, the thing that was the problem before, right? If I have this thing is already its own SVD because it's like a simple matrix, right? And this is actually this nice SVD, this rotation correct rotation corrected SVD, and this sigma 3 is -1. So what will happen here? This will be 0, this will be 0, and this will be -2. So here you can see that this energy really is properly penalizing the inversion. I guess you could forget about this thing. If you already have an SVD routine that gives you proper rotations U and V. Most SVD routines give you just orthonormal matrices, which means that you can have a reflection in both U and or V, in which case you need to play this trick to get it to this form. But if you already have an SVD routine and FTQS has a very nice optimized routine for SVD like this, then you don't have to worry about it because it already gives you this nice form which we need there. By the way, there's a different way to write this. I can also say that this is equivalent to U prime sigma prime U prime transpose minus U prime V prime transpose. Why is that? Because these are rotations, so if I multiply from the left and from the right with rotation, the Frobenius norm does not change. The property of Frobenius norm. And this is back my deformation gradient, right? And this is nothing but the best fit rotation we have already been talking about in some previous lectures. So the alternative way I can write this is F minus R, where this R is exactly the R from polar decomposition. If this is my polar decomposition, R is a proper rotation, and S is a symmetric matrix. So this energy is exactly equivalent to the difference between F and the best fit rotation to F. So what I mean by best fit rotation, this R turns out to be such a rotation matrix which minimizes this formula, this Frobenius norm, the distance from F in the Frobenius norm. The other way you can look at it is if I write the SVD, U sigma VT, what I can do is I can just stick in here VVT, right? So that becomes U VVT sigma. I want to stick there VTV. So it becomes U VT V sigma VT. And I can say, hey, this is my R and this is my S, because this is clearly symmetric, right? If I transpose this, I get the same thing. And this, if both U and V's were rotations, then this is also going to be a rotation, so this is exactly polar decomposition. This is how you get polar decomposition from SVD. And you get a proper polar decomposition, I mean proper rotation matrix, true rotation matrix, if this was the rotation fixed or rotation consistent SVD. And this is the way how to correctly penalize inversions. Now if you have inverted element, this energy does not like it. Essentially says there is a lot of elastic energy stored in such an element, so that means there will be restorative forces that will push to uninvert the element. Okay, did I confuse you enough? Okay, in that case, I will now let you go. We will continue next week.